In this lecture, we would like to discuss lexical semantic indexing, or rather latent semantic indexing, and this is a way of capturing co-occurrence amongst words and thereby doing more effective language processing and information retrieval tasks. So, as the title says, we would like to discuss least square method, then we would like to have a recap of the principal component analysis and then slowly move towards latent semantic indexing. So, latent semantic indexing is a way of dimensionality reduction. So, this is a very important task to find out which attributes actually are critical for a classification task, which features play a very important role, and the idea is to take a combination of these attributes and features and thereby work with a smaller number of attributes and features. We must note that the attributes and features are not dropped, but they are merely combined to obtain a smaller number of changed attributes and features. So, related attributes and features are combined to reduce the number of attributes. The result is a more effective classifier. This is achieved by a technique which we will discuss called singular value decomposition, and we will slowly introduce this through the least square method and principal component analysis. So, first we take a very simple problem, the problem of fitting a line given a set of points, and this is done by what is called the least square method. We follow here the discussion given in Manning and Schutz's Foundation of Statistical Natural Language Processing 1999. So, what is given is a set of n points x 1 y 1 x 2 y 2 up to x n y n, and our task is to find a line f x equal to m x plus b that best fits the data. Now, why we would like to get this line, and what does it have to do with dimensionality reduction, attribute reduction, we will see very soon, but we are saying that our task is to simply fit a line to a set of n points. Now, when we have this line f x equal to m x plus b, what varies is these two values m and b, and we try to find out m and b such that the line best fits the data, and m and b are the parameters to be found. Now, what is the meaning of the line that best fits the data? The line that best fits the data is the one that minimizes the sum of squares of these distances. Okay. So, we would like to find a line such that the points which are given x 1 y 1 up to x n y n, these points are at least distance from the line. So, the sum square distance of each point from the line is taken and minimized. So, we can see that f x I is the value given by the line. F x I for a particular value of x, f x I is the value given by the line. The actual value is y. Okay. So, y minus f x I is the difference. If we take its square and sum it up, then there is no interference from change of sign. So, y I minus f x I is a measure of error. The square of this error is summed up from 1 to n for all these n points, and the sum square distance is nothing but y I minus m x I minus b whole square, I from going from 1 to n. So, this is the quantity which should be minimized, so that the line best fits the data. Now, how do we minimize? we take partial differentiation of these sum square distance with respect to b and m, and if we do so, we get b equal to y bar minus m x bar, and m is this expression. So, for clarity, let us do this derivation quickly. Now, we have S S m b is equal to sigma y I minus f x I square, which is equal to y I minus m x I minus b square I equal to 1 to n. Now, delta S S with respect to delta b will be nothing but sigma I equal to 1 to n y I minus m x I minus b into 2 into a differentiation for minus b, which will be minus 1. Okay. So, this is equal to minus 2 into sigma I equal to 1 to n y I minus m x I minus b. So, this partial derivative should be equated to 0 for minimization, and therefore, we have minus 2 sigma I equal to 1 to n y I minus m x I minus b is equal to 0, or I equal to 1 to n y I plus m x I equal to 1 to n plus b n equal to 0. Okay. So, this is the first equation after taking partial derivative with respect to b. If I take the partial derivative with respect to m, then delta S S delta m equal to 2 into I equal to 1 to n y I minus m x I minus b into minus x I to minus x I. So, equating to 0, we have I equal to 1 to n y I minus m x I minus b into x I equal to 0. So, this is equation 2. So, equation 1 was this sigma I equal to 1 to n y I plus m sigma I equal to 1 to n x I plus b n equal to 0. Actually, this will be minus, this will also be minus, this will be minus. Okay. So, this is what it comes out to be as equation 1, and equation 2 is this. So, from these two we can get this expression, which is b equal to y bar minus m x bar. So, b n was equal to sigma y I minus m sigma x I. If you divide by n, then sigma y I by n is y bar, sigma x I by n is x bar. So, b is equal to y bar minus m x bar. And similarly, m can be processed and the value of b can be put here, and we obtain m to be equal to I equal to 1 to n y bar minus y I into x bar minus x I divided by I equal to 1 to n x bar minus x I whole square. Okay. So, what is this quantity? This quantity is nothing but the variance, and this quantity is something like the covariance. So, this is like the covariance and this is the variance. So, this captures the difference from the mean, and this captures the difference from the mean for individual variables and takes their product, okay, and B is equal to y bar minus m x bar. So, given the data, we can very easily find out m, and having found m, we can find out the value of B, because the mean of the values are known from the data. Okay. So, we take an example here. These points are given 1 1 2 2, 6 1.5 and 7 3.5. These 4 points are given. So, this is 1 1, this is 2 2, this is 6 and 1.5, and this is 7 and 3.5. So, these 4 points are given, and we would like to find a line which best fits the data. So, by doing the analysis which we have shown before, we can find out the individual means of the x coordinates and the y coordinates. From the individual means, we can find out the m value as covariance and variance, and then we can find out B. So, the line y equal to 0.25 x plus 1 is the best least square fit for these 4 points, okay, which can be very easily find out. So, this is the line with slope 0.25 and intercept on the y axis as 1. Okay. So, this line is found out. Now, the question is, as far as machine learning is concerned, dimension reduction is concerned, what does it bring to the plate? What do we gain by doing this least square fit? The next slide shows this, the implication of the line fitting. So, if you look at this diagram, then these 4 points are 1, 2, 3 and 4. These are the 4 points, and their projections on this best fitting line are A, B, C and D. Okay. So, these are the projections and this is the line. Okay. So, what do we gain from this from classification point of view? Now, imagine that these points 1 and 2 belong to one class, call it the positive class, and 3 and 4, these 2 points belong to another class, call it the negative class. Okay. So, these 2 belong to 2 classes. So, there is no problem in setting up a hyperplane or a line. In this case, since it is 2 dimensional data, one can put a line this way and separate the 4 points. Okay, 2 points in one class, the other 2 points in the second class. Now, this decision is based on 2 attributes, namely the x and y values of A, B, C, D. Okay. So, all the 4 attributes are involved in this classification. Suppose we do it in a different way. What we say is that we would do the same task in the one dimension, Okay. So, what we will do is that we will look at the projections of these points, and we will form another attribute from these points. Okay. We will call these attributes the distances of their projections on the line from O. Okay. This is the point O, and the projection of one is A on the line. This distance of A from O is the attribute considered. This distance of B from O is the attribute considered, similarly for C and D. So, now each point, instead of having two specific pieces of information, okay, have one specific information. Okay. So, which is a particular constructed information, which is that there is a point O which is special for this, and the distance of A from this point, of B from this point, of C, of D from this point. So, see how the dimensionality of the problem has been reduced. Okay. So, right now the decision was with respect to 2 attributes of each point. After we decide that the new attribute is distance from O of the projection on this line, we are dealing with only one piece of information. Okay. There is only one dimension which is to be considered now, and this is the heart of the problem. This is the heart of the point discussion. From multiple attributes, we obtain a reduced set of attributes and base our decision on that. Okay. So, now when we talk about dimensionality reduction, there is a misunderstanding. The misunderstanding is this: people think that we reduce the number of attributes. We do not reduce the number of attributes. What we do is that we construct a new set of attributes, okay, based on the given set of attributes. Just like from the attributes x and y, we obtained a new attribute called the distance from O of the projection. Okay. So, let us remember this point and let me write it down. Okay. What does dimensionality reduction mean? It does not mean that original set of attributes or independent variables are reduced. No, it does not mean that. Okay. It does not mean that original set of attributes or independent variables are reduced. Okay. What it means, new attributes are constructed from old attributes and decisions are made based on these new attributes. Okay. More importantly, these new set of attributes are less in number than the original attributes. Okay. So, this is the fundamental of dimensionality reduction and is at the heart of latent semantic indexing. And let me repeat this, that the original set of attributes transform into another set of attributes which are functions of these original attributes. Okay. So, diagrammatically speaking, you have A1, A2 up to AM. So, all these go through a transformation and produce B1, B2 up to Bm. Okay. M is less than n, okay, and this is the heart of dimensionality reduction. Okay. Fine. So, if this point is understood, let us look at this very important diagram again. We have a set of attributes here going through a transformation, giving rise to another set of attributes B1, B2, Bm. M has to be less than n, otherwise there is no dimensionality reduction. Now comes the question of what this box does. Okay. The technique of transformation. Okay. What is this technique of transformation? This is the question, and there are different techniques. Okay. So, looking at the slide again, what was the technique of transformation here? The technique of transformation was we took these points, projected them to this line, okay, and the distance of the projection from this point O was found out. How was it found out? It was found out from the original attributes x and y. After projection they became something, and those values then gave rise to this distance attribute. Okay. So, this was one technique. We go to another very well known technique called the principal component analysis. Now, the difference between principal component analysis and singular value decomposition is that both of them are for dimensionality reduction. The number of attributes get transformed into another set of attributes, and this new set of attributes is less in number. Now, principal component analysis is applicable only to square matrices, okay, whereas singular value decomposition is applicable to any general matrix. Now, what is the idea behind this? Let us first motivate this particular problem. So, in NLP and IR, a structure that plays a very important role is term document matrix. Okay. So, this is a structure which plays a very important role. So, this term document matrix has the following shape. There are these documents D 1, D 2, D 3 up to D n, and there are words in the vocabulary of the language, word 1, word 2, word 3 up to word m. So, any w I j, okay, let us call this matrix as A. So, any element A I j is equal to weightage of word I in document D j. Okay. So, the weightage of the word I w I in document D j. Now, if the document, if this matrix is only expressing term presence or absence, then it will be filled with ones and zeros. Otherwise, there are different schemes for giving weightage to words with respect to a document. Okay. So, this we can see later. So, now this A matrix, which is W 1, W 2 up to W m with columns D 1, D 2 up to D n. What has dimensionality reduction got to do with this particular matrix? So, in this matrix, the objects are the documents D 1, D 2 up to D n, okay, and their attributes or features are these words W 1, W 2 up to W m. So, these words are the features and the documents are the objects. Now, so we note this down, documents are objects, words are attributes or features. Okay. So, decisions based on these documents appear in many forms. So, decisions based on these documents appear in many forms. One could be document classification. Okay. Two could be information retrieval on these docs. Okay. So, these documents may be ranked after information retrieval, and this ranking and scoring depends on these documents properties. So, classification and retrieval happen to be important tasks on these documents. Now, each document is represented by a feature vector, and in this case the term vector. A document J is represented by A 1 j, A 2 j, A 3 j up to A m j. Okay. So, the weightage of these terms W 1, W 2, W 3 up to W m in the document D j. Okay. So, each document has become a feature vector and the decision is made based on this feature vector. Now, the dimensionality reduction question, is it possible to get a different feature vector for a document, okay, that is reduced in size, okay, that is reduced in size. This is the question. Is it possible to get a different feature vector for a document that is reduced in size? So, this means, what it means is that the document which was A1j, A2j, A3j up to AMJ, can it be reduced to a reduced document B1j, B2j, B3j up to Bkj, where k is less than m. Okay. So, this is the formulation of the problem. Can we reduce this document vector to a reduced vector going from the space of A's to B's? This is the dimensionality reduction question for the document. The question that naturally arises is why. So, expect that the reduced vectors will be better for all decision making on these document objects. We expect that the reduced vectors will be better for all decision making on these document objects. Okay. This is the purpose of dimensionality reduction, and the foundation is Occam-Razor principle. Okay. Hypothesis based on compactor data is likely to generalize better. Okay. So, the hypothesis which is based on compactor representation of data is likely to generalize better. Now, what did we understand from our discussion? That the attributes A1, A2 up to AN give rise to B1, B2 up to Bm, m less than n. So, now in case of term document matrix, okay. So, this is the picture for dimensionality reduction from set of attributes A1, A2 up to n, we go to B1, B2 up to Bm, m less than n. Now, for term document situation, the words W1, W2 up to Wm, okay, after transformation, after dimensionality reduction, give rise to entities U1, U2 up to UK, okay, UK, where k is less than m, and this U1, U2 up to UK. So, each UP is a function of W1, W2 up to Wm. Okay. So, each attribute UP is constructed from the terms W1, W2 up to Wm. Now, the question is, what is UP? Okay. What are these U1, U2 up to UK? So, that is the interesting question in language processing scenario. Okay. For other problems, all these new attributes which are constructed from old attributes have different meanings, but in natural language processing situation where the attributes are the words and the new set of attributes have been obtained, these new attributes UP are cluster of related words. Okay. So, this is the heart of dimensionality reduction, again in natural language processing. Okay. This is the cluster of related words. In particular, they are co-occurrences. Okay. So, we have hit upon a very important concept in natural language processing. Dimensionality reduction has been applied. Okay. The dimensionality reduction has been applied. We have got these words occurring in various documents. We have applied dimensionality reduction, and what we have obtained is a set of new attributes. What these new attributes are? Very strongly co-occurring words. Okay. For example, if these words are astronaut, cosmonaut, car, vehicle, etc., then we will see that related words like cosmonaut and astronaut, they will be grouped together in terms of, let us say, U1, car, vehicle, okay, automobile, they will be grouped together, let us say, in U2, okay, with their specific weightages. And thus, we have, after dimensionality reduction, a set of cluster of words, and these cluster of words are better for decision making on the document. So, that is the point. Now, instead of decision making on individual words, we capture these relationship between words, and these related words are used for decision making. So, we say that we have captured the latent relationships. We capture the latent relationships amongst words. Okay, that is where the term latent comes. They were latent in the words. Latent relationships are captured, and in specifically in IR scenario. Okay, in IR scenario, instead of this index table, which is W1, W2 up to Wm, we will have another index table, which is U1, U2 up to UK. So, this is word based, this is term or word based index. Okay. So, this is on the other hand latent, this is latent index, okay, but this also captures some semantics in the form of word relationships, that is why it is called latent semantic index. Okay. So, this is the importance of the word association, word co-occurrence, giving rise to latent semantic index. So, instead of retrieving documents based on this, we retrieve documents based on this, and thereby become more accurate. Okay. So, this was in the context of natural language processing information retrieval. Now, we get an idea about what the exact mathematical techniques are, and this is facilitated by looking into the details of this important topic called principal component analysis, PCA. As remarked before, this is for square matrix. We take an example of a very famous machine learning problem known as the iris data, okay. And we show here only 3 out of the 150 data points. Now, there are 3 classes called iris setosa, iris versicolor and iris virginica. These are 3 classes of flowers, and the idea is to classify a particular flower into one of these 3 classes. The deciding attributes of such classification problem are petal length, petal width, sepal length and sepal width. So, for example, the flower with ID 001 has a petal length of 5.1 units, petal width of 3.5 units, sepal length of 1.4 units, sepal width of 0.2 units. Then and it is classified as iris setosa. So, this way flowers with 150 IDs 0001 to 150 are given with these values of these 4 attributes. Now, this data is a very famous data and has served as a benchmark data for any machine learning problem. Whenever anybody designs a new machine learning algorithm, one of the important tests for the algorithm is performance on the iris data. So, what is done is that all these 150 data items are divided into the training data and testing data. So, typically 80% of the data is used for training, 40 items from each class are taken for training. So, that makes totally 120 training points. Testing is on remaining 30 data items. So, the question we ask is, do we have to consider all the 4 attributes for classification? Okay. Maybe the attributes can be combined in some interesting way, okay, and then decision can be taken. So, less attributes is likely to increase the generalization performance. This is the Occam-Razor hypothesis. Okay. So, now we discuss how to deal with multivariate data in the context of principal component analysis. So, we have these attributes x1, x2, x3, x4, x5 up to xp, and there are these n data points with values x11, x12, x13 up to x1p, x2p, 21 up to x2p and so on. So, each object has these values under individual attributes. Now, some preliminaries are useful here in understanding the technique. We get the sample mean vector, which is mu1, mu2, mu3 up to mu p. For the ith variable, mu I is nothing but sigma j equal to 1 to n x I j divided by n. Okay. So, for ith variable, this is the mean. So, what this means is that for this particular attribute, let us say x3, we will sum up all these values and divide by n to get the mean for the attribute x3, which will be mu 3. So, mu 1, mu 2, mu 3 up to mu p are obtained for each of these attributes. The variance is also obtained for each attribute. Sigma I square is nothing but the departure from the mean. Okay. So, x I j is subtracted with mu I, the attribute mean, the square is taken and it summed up from j equal to 1 to n and is divided by n minus 1 to give the variance. So, again if you go to the table, we have already calculated the mean and we see the difference of each value from the mean. Okay. Take its square, sum it up, divided by n minus 1 and we get the variance. The next important parameter is the sample covariance, which is nothing but the covariance between two columns, okay, two different attributes. So, if we have x a and x b, then what we do is that we take the difference of the ath attribute from the mean, the bth attribute from the mean, take the product, take the sum from j equal to 1 to n, divide by n minus 1, and this gives the sample covariance. So, again coming to this multivariate data, if I want to find out the covariance between x1 and x2, I have the mean from this column, I have the mean from this column. So, I have the departure also from the mean for each value. So, corresponding rows, I take this difference, multiply, sum up all the differences, divided by n minus 1 and thereby get the covariance. So, covariance between any two attributes is measured this way. This measures the correlation in the data. In fact, the correlation coefficient is nothing but R A B, which is equal to the covariance between A and B divided by sigma A and sigma B, product of sigma A sigma B. Okay. C A B by sigma A sigma B, that is covariance divided by standard deviation of the two attributes. So, this is the correlation coefficient. After that, we do what is called standardization on the variables. We replace each value by this new quantity y I j, which is x I j minus mu I divided by sigma square. Okay. So, if you go to this table once again, each value is subtracted from the mean and is divided by the variance. Each value is treated this way. So, this does a standardization of the variables. Then we get the correlation matrix, which is 1 for all the diagonal elements, because the correlation between a row and itself, between an attribute and itself is surely 1, and after that the correlation is expressed through R 1 2, R 1 3, etc. So, what is the meaning of R 1 2? The meaning of R 1 2 is the correlation coefficient between attribute 1 and attribute 2. R 1 3 is between attribute 1 and attribute 3, which you can find out very easily from the column values, their mean, their variance, and the product of and the covariance. Okay. So, this gives us the correlation matrix. Now, we need two important concepts, which are eigenvalues and eigenvectors. So, A x equal to lambda x is the definition of the eigenvalue. So, where lambdas are the eigenvalues, and for each lambda we get the eigenvector. So, this a 1 1 x 1 a 1 2 x 2 up to a 1 p x p is equal to lambda x 1, a p 1 x 1 a p 2 x 2 up to a p p x p lambda x p. So, these are the equations obtained from A x equal to lambda x, the defining equation from eigenvalue. So, these lambdas are solved, and from there the eigenvectors are computed. So, from these eigenvalues and eigenvectors we will proceed to principal component analysis, then to singular value decomposition, and then to latent semantic indexing. This is for the next class.